This is my favorite thing to teach. It would be your hardest course, though. So, this is my name, this is my email address. Feel free to send me emails at any time. The course is going to have 2 teaching assistants. Both of them are PhD students working on algorithms. So, John Lam and Karim Kochekov. Again, their emails, feel free to send messages whenever. If you have any questions, anything is unclear. We're going to have a bunch of guest lectures by Dr. Harshid Mutwani. He's going to actually cover some extra things that I'm going to assume you already know from 2711 and other courses. But if your theoretical background is not that strong, definitely attend these courses, these lectures. These guest lectures are in addition to the normal lectures, and they're not compulsory, but highly recommended. Now, let me talk a little bit about grading, and also when you come in, please close the door. I don't want to do this. Okay, so grading in this course is very different from 3711 and also previous editions of the same course. So we're going to have 4 homeworks. And also you don't need to take photos or write down anything. I will put all of these on Canvas. And yeah, generally you don't need to take notes. I take notes for you and I put everything on Canvas. So, that's a separate problem. Hopefully you will have Canvas access by the end of the day. So we're going to have 4 homeworks. And in the homeworks, generally, you're going to be asked to design some algorithm to solve a particular problem, and then also code it. So each homework accounts for 10% of your total grade. It's really important that you write your algorithms clearly and prove that they are correct and prove that they have the desired runtime bounds and everything like that. But it's also really important that you can code everything. We will also have a midterm exam. This is 30% of your grade, and a final exam, which is another 30%. And the exams are entirely theoretical, so you just have to write with pen and paper. There are some required coding practices. They don't count for anything, but if you miss them, you will get an F. Okay? So it's 0%, and they're generally easy. And they have very long deadlines, so it's really hard to miss these. Like, I don't expect anyone would have this problem. The other thing is we have a resubmission policy for our homeworks. So we release the homework, there is a deadline, you submit your solutions by that deadline, then you get feedback from myself or the TAs, and then you get to submit again. And then your final grade would be the maximum of the 2 attempts. So again, really hard not to get an A. Yeah, so this is simultaneously the hardest and the easiest course. So it's really easy to get an A if you really put a lot of effort, but then it needs a lot of effort. We expect a lot of self-study and coding practice. The coding practice I already told you about here, but for self-study I will put tons of things on Canvas. Again, all of these are not required, just recommended, but very highly recommended. And since this is an honors course, I'm actually going to skip over a lot of the content that is covered in the normal version of this course, and I'm just going to give you YouTube videos to watch. Okay? So now you can risk it. You can say, I already know all these things. I don't want to watch these YouTube videos, but it's a risk you're taking on your own. We will put a lot of resources there. For those of you who use Python, I'm very sorry. We're going to use C++ in the entire course. We are a monolingual course because I couldn't convince the TAs to learn more languages. So we use C++ for coding in all the classes and tutorials. We also expect you to write C++ code in homeworks. This is the university policy that you're not allowed to use ChatGPT or whatever. I don't think they will help you in any way in this course, but I mean, honestly, I would be impressed if you can make ChatGPT work here. Yeah, we're giving all of the homeworks to ChatGPT to make sure it cannot solve them. So it's just easier if you solve it yourself. Okay, with all of this out of the way, let's actually start the first lecture. With runtime analysis of algorithms, and already in this session you will see how the lectures are going to go. I teach you something, then I code it for you, and then we continue like that, and there's a mixture between tutorials and lectures. So unfortunately you have to attend all the tutorials as well, because I teach there too. But then on the other hand, everything will be recorded and put on YouTube and Canvas. But please don't get this as any kind of encouragement for not attending. Okay, so today we're going to start talking about runtime analysis of algorithms. Now, normally these courses start by saying what an algorithm is. I assume you know that. So let's do runtime analysis. So here's the idea. Let's say I have a program, not necessarily an algorithm. Let's say I have a program P. So my program is going to take some input, and it's going to take some steps, execute some commands, and hopefully it's going to terminate. Generally, in this course, if a program doesn't terminate, we consider that to be an error. Okay, so what is the runtime of my program? Now, this can actually get a bit philosophical, because what do I mean by time? Like, how do you even measure time? But on a more fundamental level, if I run the same program on different machines, I'm probably going to get different runtimes, right? And also, if I have a program or an algorithm that takes, let's say, 5 minutes today, maybe in a year or two from now, we have better hardware, and then it takes 2 minutes instead of 5 minutes. So we have to make runtime analysis much more formal and mathematical, so that we can actually talk about the runtime of an algorithm in a way that is independent of the machine that it's being run. Now, so here's what I can do. I can say I have a bunch of operations. Let's say the most fundamental and atomic operations that my CPU can perform. Let's say I have operations like adding numbers, multiplying numbers, shifting bits, things like that. And I just count how many of these operations my algorithm is going to perform. Okay. So if I have a set of atomic operations, so let's say I have a set A of atomic operations. And let's say I also have some algorithm or some program, and I use algorithm and program to mean the same thing. So I have an algorithm, big A. So I want to define the runtime of this algorithm, but of course I will have different runtimes on different inputs. So I have to also specify what is the input that I'm giving to this program. So I define it like this. I say T of A and I is going to be the runtime of my algorithm A if I give it input I. Okay? And by runtime, I just mean how many atomic operations it performs until it terminates. And if it never terminates, I say the runtime is infinite. Okay? So T of AI is going to be the runtime of A on I. By the way, this is the easiest session of this class. This is not representative. Okay? So this is just the number of atomic operations. Well, this is good, but we are assuming some things here. The first thing I'm already assuming is that the number of atomic operations only depends on the input. And we will soon see algorithms where this is just not the case. Maybe I have an algorithm that is doing something, I don't know, maybe it's flipping a coin, doing something random, and on the same input it has many different runs. So what happens if I can have many different runs? Then this kind of definition doesn't work. And then the other problem with this definition is that I'm assuming that all the atomic operations are equal. But maybe some of them actually take more time in the real world. Right? So if you're working with integers, probably shifting is cheaper than multiplying two integers. Right? But I'm ignoring all of that. I'm just counting the number of atomic operations. And the worst part of this definition is, of course, that my time depends not only on the size of my input, but on the entire input. So I would prefer to be able to analyze the runtime of my algorithm only based on the size of the input. And I'm sure you've seen these things before, like we say an algorithm is linear, quadratic, blah, blah, like the runtime is O(n) squared. That n there is the size of the input. So I don't want to talk about any particular input. I want to be able to talk about inputs of the same size. So first of all, I'm going to define the size of my input, and I'm going to say that I show it with n. Now I have to be kind of formal about this. So in the most formal sense of the word, the size of my input is the number of bits that I need to encode my input. So how many zeros and ones are going into the input. But in this course, we're not going to be that formal, and for a bunch of different inputs, we look at different things. So if my input is an array, I would just use n to show the size of the array, the number of elements in the array. If my input is a graph, I'm going to use n to show the number of vertices of the graph. If my input is a string, I'm going to use n to just show the number of letters in the string, and so on. Now, this is not exactly the same as the number of bits that you need to write down this input, but for our purposes, this is good enough, and you will see why. Okay. Now, assuming that I can assign a size to every input, I want to ask, what is the worst case scenario? So if I know that the size of my input is n, what is the worst possible input? What is the input that gives me the largest possible runtime? And I'm going to take that, and basically I'm going to use that for my runtime analysis. And this is what we call WCET, worst case execution time. And basically the idea is this, that I want to define, I reuse T, but you know what I mean. So I want to say that the runtime of algorithm A on an instance of size n, I'm going to define this to be the maximum over all instances that have that size. So I'm overloading T here, but that's fine. Okay. So now I can say the runtime of my algorithm is n squared, or whatever. The runtime of my algorithm is n. Okay. Nice. But this is still not solving another problem that we had. So it solves the problem that our runtime dependent on our entire input and not just on the size. Now I'm just saying for every size, just take the maximum possible runtime. So now I can talk of runtime based on size. But I still have the problem that the runtime is going to be different on different machines. Right? I'm defining my runtime as the number of atomic operations, and maybe that's the same if the machines have the same set of atomic operations. But at the end of the day, different machines are going to take different amounts of time on each atomic operation. And maybe some machine is better at addition, some other machine is better at shifting. And you have no idea of which one's the case, and this is definitely dependent on hardware. And if there is one thing in this course that we don't want to do, it's getting into how hardware works. So we want to keep it entirely on the mathematical and software side. Okay. So this is where asymptotic runtime analysis comes in, and this is one of the things that I assume you have already seen, so I'm going to go over it really fast. So the idea is actually very simple. Asymptotic analysis. Let's say I have two different algorithms, and let's say that I show the runtime of one of my algorithms with F and the other one with G. Okay? So I have two algorithms. and one of them has a runtime of f of n, and the other one has a runtime of g of n. And we have defined runtime based on n already up there. Okay. Now the question is, when would I prefer the first algorithm to the second? When would I prefer f of n to g of n? Now we can do some simple examples. So let's say I have an algorithm whose runtime is 5n plus 5, and I have another algorithm whose runtime is 100n. Right? Which one would I prefer? Now, the thing here is that I want it to be independent of the machine that I'm working with. So I don't really care about constant factors. So if the runtime is 5n plus 5, if I have a machine that is twice as fast, that would make it 2.5n plus 2.5, right? So these constants will change based on the machine. So generally speaking, I don't care about the constants. So if I have 100n, I want to look at that as just n, right? Another way of looking at this is that in a few years, the computers will be 100 times faster anyway. So if I have an algorithm whose runtime is 100n today, in a while, it will be just n. So I also don't care about this. And also, like, if I don't care about this constant factor that is being multiplied by n, I definitely don't care about this additive thing, which is much smaller. Right? So I'm going to cancel these smaller terms as well. And basically, from my point of view, both of these runtimes are linear. Both of them are just n. Now, we want to formalize this kind of hand-wavy cancellation of constants. And this is how I formalize it. So this is our formal definition. I would say that the function f is in O of g of n, or in O of g, if it satisfies the following constraints. But before that, I have to make something very clear. For every function g, I'm going to create a set which is called O of g, and this is the set of all functions that are at least as good as g. Okay? So it's very important that you understand O of g is a set. It's not just a function. We sometimes, especially in a lot of older textbooks, you would see that people write f equals O of g. That's because the old typewriters didn't have the sign for like this epsilon thing, inclusion. So f is actually a function, and O of g is a set of functions. So f is in O of g if f is better than g. Now, when do I say f is better than g? Well, let's start by saying that I want f to be less than g. Right? Now, of course, I can say that I want this for every n. So for every size, I want to say that f is less than or equal to g. If I have that, then I would definitely prefer an algorithm with runtime f to an algorithm with runtime g. But we said we don't care about constant factors. So maybe instead of saying that f is less than g, I can say f is less than or equal to some constant. And it's really hard to write on this surface. Okay, c times g. So I just say, I'm changing my definition, and I'm saying that there exists some c. And of course, this c should be positive. Such that for every n, f is less than or equal to c times g. This is just canceling out the constants. But then there is another issue as well. I really don't care about small inputs. Because honestly, if you have an input which is very small, if you have an algorithm that, let's say, works with inputs of billions of entries, and then you have an input with like 5 entries, it doesn't matter if your algorithm is not really efficient on these small inputs. Because at the end of the day, for small inputs, it's going to take a very small amount of time. So I want to also basically forget about all the small inputs. Now, how do I do this? The way I do it is that instead of saying that this inequality should hold for every n, I just say it should hold for n's that are greater than some number, some n0. And then I say there exists such an n0. Okay? This is our formal form, our final form of the definition. So basically I say f is better than g, or at least as good as g, if after ignoring some constant factor and after ignoring all the input instances that had size n0 or smaller, f is less than g. Okay? So that's just the intuition for O. And now we have the opposite thing as well. So you can also define the set of functions that are worse than g, or at least as bad as g. And we can do it like this. That's actually called omega. So this is definition 2. I would say f is in the set omega of g, and I cannot write Greek at all, so this is omega. If basically the same thing, like there should be some n0, so I'm ignoring all the instances that have a size of less than n0, and then there should be some constant c, such that for every input that has a size bigger than n0, f of n is now, I want to say, greater than g of n, but I also want to multiply the c, so I have to multiply the c here, actually. Okay. And, I mean, it's super trivial to see that f is in O of g if g is in omega of f, and so on. Okay. Now, we have a bunch of other definitions. I'm not going to write them down like this, but basically we have small o, small omega, and theta. I'm just going to write it here. Definition 3. I say f is in theta of g if and only if f is in O of g and g is also in O of f. Okay. So this basically means that after ignoring some constant number of small inputs, f and g are within a constant factor of each other. So if f is, for example, 2n squared and g is 5n squared, they're within a constant factor of each other. And when I say f is in theta of g, basically from my point of view in analysis of runtimes, f and g are indistinguishable. They're literally the same for me. Okay? And then definition 4, let's say, I say f is in the small O of g if f is in the big O of g and g is not in the big O of f. Okay? So when I say f is in the small O of g, I mean that f is literally really better than g. And it's not just by a constant factor, like f is really better. And we have the opposite, which is small omega. F is in small omega. This is not w, this is small omega of g. If f is in omega of g and g is not in omega of f. Again, you can write all of these things with O, and we're generally going to just use big O and theta. Those are the two things that we use. Okay. Now we have all of these things. This was just a refresher from the things that I hoped you already know. Now, of course, we prefer algorithms that are faster. So in this course, generally what we want to do is we want to analyze a problem and find an algorithm that has the best possible worst case runtime. Now, at some point we will talk about other things. There is a notion of best case runtime where here they take the minimum. I think that's a stupid thing. I don't know why people even teach it. No one uses it. Like, what is the best case runtime of my algorithm if I get lucky? Like, you will not get lucky in the real world. So we only care about worst case runtime, but at some point we will talk about randomized algorithms. And if you have a randomized algorithm, an algorithm that can basically flip a coin, then it makes sense to talk about the average case runtime. Now, if I don't have a randomized algorithm in this case, it doesn't really make sense to say what is my average runtime, because you don't get to choose your input. So you have to always be negative, and you have to always assume that the user or the environment is going to give you the worst possible input. Okay. Yeah, let's start with some really trivial algorithms for the first session. Again, this is not representative. If you want to drop the course, don't let this dissuade you. Okay, so the first algorithm we want to look into is just simply computing Fibonacci numbers. Okay, so Fibonacci numbers. I always forget how many n's there are. I hope I'm writing this correctly. Okay. So the Fibonacci numbers, as I'm sure you've already seen before, are defined very simply like this, like f0 or, I used f for functions before, but now I'm just using it for the Fibonacci sequence. f0 is 1, let's say, f1 is also 1, and after that point, every fi is just fi minus 1 plus fi minus 2. This is for every I that is at least 2. Okay. Now, this is the way that a mathematician would define the Fibonacci numbers. Now, we can turn this immediately into an algorithm, and I'm going to do the stupidest algorithm that I'm going to do in this class. And by the way, when we write algorithms, we always use pseudocode, and you have to make sure that when you write your algorithms, you add enough explanation in English to make it understandable to the TAs. So here's my simple algorithm. I'm going to have a function. Let's call this function fib. It's going to take some number n, and it's simply going to apply these conditions. So it's just going to say if n is 0 or n is 1, then just return 1. And otherwise return fib of n minus 1 plus fib of n minus 2. Okay. Let me actually write this. Oh, what happened to my terminal? Why can't you see my terminal? Okay. Okay, so let's just write this in C++. I'm going to do a very simple thing here. And also, I'm not this slow in typing. I don't have my keyboard. Okay, so I'm just going to read some number n, and I'm going to write the nth Fibonacci number. Okay, and let me write the Fibonacci thing here. I'm taking some number n. I'm saying if n is 0 or n is 1, return 1. Otherwise, just return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay. Now, of course, for those of you who have some experience with C++, you already know that we have a problem with this value here overflowing and not fitting into an integer. In this course, we don't care about those things. When you write your codes, you have to care about them, like in the homeworks and so on. But here, I just want to talk about the runtime. So just imagine that that doesn't happen. So when the number n is large, of course, the output here would just be garbage because it's going to overflow. But let's see. Let me just compile this. And let me actually run it. And let me ask it to compute Fibonacci of 5. Okay. So as you see, it didn't take much time. Probably most of this time was spent just loading the machine and so on. But what if I ask for 20? This is also fast. What if I ask for 600? So you see, there was not much difference between 5 and 20. But for 600, I don't think it will end in our lifetimes. So actually, let's see where I can go. 25, 50. 50 is kind of questionable, so let's say 40. Yeah, 40 is doable. I mean, the output is wrong because it has overflown, of course. But as you see, the time is growing exponentially, literally exponentially. So, of course, I didn't measure the time exactly, and it also included the time it took me to type these things. But you see that when n was 5, f of n was computed really fast, also for 20. For 600, it will probably take forever, and so on. Now, let's actually analyze this. How much time do I actually need to compute this? Now, this is our first example of a recursive algorithm. And I can visualize this as a tree. I can visualize it like this. When I call Fibonacci on n, what's going to happen? If n is 0 or 1, it's going to finish immediately and give me the answer. Otherwise, it's going to call itself recursively on n minus 1 and n minus 2. Right? But then what happens? These two calls are completely separate from each other. They have no information of each other. So this one is going to call itself on n minus 2 and n minus 3. This one is going to call itself on n minus 3 and n minus 4. And this is going to continue, right? But you already see the problem. The problem is that I'm computing f of n minus 3 both here and here. And for f of n minus 2, I'm computing it both here and here. So I'm recomputing the same thing over and over again, and actually it gets worse as we go down. So I'm computing n minus 4 here, but also once as a child of this n minus 3, and once as a child of this n minus 3, and so on. So what actually is our runtime? So let's show our runtime by t of n. So let's say t of n is the amount of time that this algorithm takes to compute Fibonacci of n. And I don't have to say in the worst case, because this algorithm just has one execution, right? So for every n, there is literally one execution, and I'm talking about the number of steps that execution takes. And I'm considering that checking an if, or checking equality, or doing or returning, all of these are basic operations that take 1 unit of time. Okay? So my t of n would be this. T of n would be 1 if n is 0 or 1. Right? Because I can just return. And technically, I shouldn't say 1, I should say O of 1. So maybe it's like 3 or 4 operations. But again, as I said, I don't care about constants. I'm going to just use O. The eraser doesn't work that well. O of 1. Okay. And then otherwise, if n is not 0 or 1, then t of n is basically t of n minus 1, because I'm calling Fibonacci on n minus 1, plus t of n minus 2, because I'm calling Fibonacci on n minus 2 otherwise. Now, as you see, this is literally the Fibonacci sequence. So to compute the nth element of the Fibonacci sequence, the amount of time that I'm spending is actually proportional to the nth element of the Fibonacci sequence. So basically what I have here is that my time, t of n, is in the theta of fn, which is the nth Fibonacci number. Yes? Yes, that's actually a good point. I forgot that. You're right. So plus 1 or plus O1. So actually, it's even worse. So the time I'm spending is definitely more than the nth Fibonacci number. Right? Now, okay. We will talk about how to solve these recurrence relations like this at some point in this course. But for now, what we know for sure is that the Fibonacci numbers grow exponentially. So this is an exponential runtime, and it's terrible. And generally in this course, we like to see polynomial runtimes, and we like to see low-degree polynomials. Now, I can easily change my algorithm so that I don't do this extra calculations, so that I don't repeat any of the calculations. I can just have an array of size n, and I can start filling the array from the beginning. So I put f of 1 or f of 0 in place 0 of the array, f of 1 in index 1, and so on, and I keep filling it. So this would be something like this. If I want to write a pseudocode, and by the way, this is the only session in which I'm writing both pseudocode and code. I'm too old and lazy for this. So I have an array, let's say A, of size n. And what I'm going to do is very simple. I'm going to say A0 and A1 are going to be 1. And then I'm going to say for every I, which is between 2 to n, actually this should be n plus 1, AI is just going to be AI minus 1 plus AI minus 2. Okay. Let me just code this. So instead of this, let's say I'm going to use a vector. Who cares? A vector is basically an array. At some point we will talk about it. I'm going to just create a vector of integers of size n plus 1. And then I have to give it a name, sorry. I'm going to say, or actually I used A in my pseudocode, let me use A here. I'm going to say that A0 is equal to A1 is equal to 1. And then for every I from 2 to n, AI is AI minus 1 plus AI minus 2. And then finally I just write AN. Okay. Let's see how much time we need now to do 600. Okay. So as you see, this was like basically instant. Now, I can, of course, scale it much more. It still works. Now, why is this so much faster? Because, well, I can just analyze the runtime, right? So how many operations am I doing here? This is a constant number of operations. And then afterwards, for every I from 2 to n, I'm literally doing 2 operations, an addition and a copying of the addition resulting together. Right? So this algorithm actually has linear runtime. So my runtime here is just ON. And of course, this is going to work much faster than any exponential time algorithm. Actually, you can even compute it for 1 billion easily. Of course, we still have the problem that our integers are overflowing. Let's say instead of finding the actual Fibonacci number, I wanted to find the remainder of the Fibonacci number when divided by some other number, so that I don't have this whole issue with overflows, and then it would be ON. Of course, at some point we will talk about what happens if I want to compute the entire Fibonacci number, because at that point you have to also consider like the length of your output, which will not be constant anymore. But for now, this is all we wanted to do. So what this shows you is actually a lesson that we're going to learn and relearn in this course. And it's that even though the course is about algorithms, it's actually much more about data structures than algorithms. So what really matters is how you structure your data. Here, I was just doing something recursive without any particular data structure, just hoping that my programming language gives me a good enough data structure. But here, I was creating the simplest possible data structure, which is an array, and saying, let's remember the values that I have computed before, and let's not recompute them. And actually, most of this course is going to be focused on how to structure the data cleverly so that you have faster algorithms. Okay. Let me give you another example, which is hopefully a little bit harder than this, but still not too hard. And this is the problem of maximum contiguous subsequence. So here's the thing. Consider a company that is making some money every year. And let's say that I'm giving you the income of this company as an array. Okay? So in the input, I'm giving you an array of integers. Okay? And so as an example, maybe the company made $10 or $10 million in the first year, then 5. Then in some years it lost some money, and so on. So I have this, and I basically ask you to find the golden age of the company. Find a starting point and an end point, such that the sum of the income in that particular segment is as large as possible. Okay? So for the output, I want you to output 2 numbers. Find 2 indices, I and j, and of course I should be less than or equal to j, such that if I take the sum of all the elements in A from index I to index j, this sum is maximized. Okay? Is the problem clear to everyone? Ask me if it's not. Okay. Now, let's just find different solutions to this. The first solution that always comes to mind is to just brute force everything and try all the possibilities, right? So if I just want to brute force everything, I can consider all possible values of I and j, and for every value of I and j, I can just run a loop that sums up this k, and then finally take the maximum of all of this. And of course, a lot of you are laughing because, of course, this is laughable. But we're going to do it anyway, because for some people this is the first algorithmic course, and for others it's not. So I'm not going to write the pseudocode here. I'm just going to go directly to the code. So let's call MCS. Actually, let's say I have this array A. I don't care what the size of the array is. I'm not going to actually run this code right now. And okay. So let's say I have some number n. Actually, whatever. Let's put a maximum n here. And let's say that my maximum n is 10 to the power of 6. That's good enough. Okay, I read an n, and then I read my array. Let's do it from 1, just to annoy some people. I read my array. Okay, and now I want to find the maximum contiguous subsequence. So I can just have an integer called my answer, let's say. And my answer starts with 0, because I can always just take nothing. Like, even if all of the entries in the array are negative, I just take nothing, and the answer would be 0. And then here's what I'm going to do. I'm going to say my I is anywhere between 1 to n. This is the start of my segment. And then I'm going to say that the end point of my segment, my j, can be anywhere from I to n. And then for this segment from I to j, I want to find the sum of all the numbers. So I just write a for loop that does this. So my k goes from I to j. And of course I have to have a variable here, which is, let's say, 0 initially, and then and here I'm going to say sum increases by ak. And then after I compute the sum, I say if the sum is bigger than the previous answer that I had, the answer becomes this new sum, and in the end I write the answer. Okay. Now, this is a terrible algorithm, of course, but what is the runtime? Now, a very simple rule of thumb is that when you have a bunch of 4s nested in each other, you can just multiply the runtime. So I have 3 for loops here. Each for loop runs for at most n iterations. So the total number of iterations is at most n cube. And in every iteration, I'm doing a constant amount of work. I'm accessing this particular array element, adding it to the sum, taking the maximum here, blah, blah. So my runtime, actually, for this naive algorithm is going to be cubic. Now, again, this is terrible, but I cannot show it to you how terrible it is because I have to create an input of this size. I'm just too lazy for that. Let's see, do we have time to do that? Just, yeah, whatever. Let me do this. So I'm just going to create an input generator. Okay. I'm going to, is it C time, something like that? I don't know. I'm going to say that read a particular n and then write n, and then for I from 1 to n, just actually I don't even care that it's really random or not, so just write a random number, whatever, because I just want to show you the runtime, right? So if I give it, let's say 10, yeah, it gives me 10 numbers. That's good. So let's try this. Let me do mcs.cpp. How do you give it the name? Small o. Yeah. Yes. Okay, so I just compiled that, and now I'm going to compile my input generator. Let's say I put my input in input.txt, and let's say I start with 100 numbers. Okay. And let's see how much time I need if I run my algorithm on 100 numbers. So I'm going to just give that input of 100 numbers, 100 random numbers. And actually all of the numbers that I'm generating are positive, so it's not even a great input. I'm going to give it, and I'm going to see how much time.
There's a typo in your previous project.
Ooh, yeah, probably. In this one?
Right, it should be J, smaller, or
Oh, yeah, right. Yeah.
otherwise you will never end.
Yeah, that's why it didn't end. Good catch. I should try writing these codes beforehand. I will do it next time. Yeah, let's give it the input, and as you see, for 100 numbers, it gave the output pretty fast. Now, let's do 1,000. Right? And let's run it again. It's a bit slower. Now, let's do 10 to the power of 5. And this one's going to take a very long while. Okay. Like, I think even 10,000 would take a very long while here. I don't know how good my laptop is, actually, but yeah. 10,000. I don't think it can do 10 to the power of 12 computations any faster. Okay. Yeah. So I have an algorithm that can basically do up to 1,000 on my laptop, at least. But for 10,000, it takes a long time, more than our patience. So how can I do this better? Well, one way is to avoid doing this calculation again and again, right? So every time I'm doing this calculation, I'm basically throwing out all the information that I had before. So if I've already calculated the sum of numbers from index I to index j, and now I want to calculate from index I to index j plus 1, I can just add the number at index j plus 1 to the previous sum, right? I shouldn't have to start from index I and do the sum again. That's really stupid. So let me fix that. So actually, yeah. So instead of doing this, I'm going to say I remove the sum from here and I put it here. So for every I start with a sum. I say my sum is 0. And then for every j that goes from I to n, I just say sum increases by aj. So now sum is always the sum of the numbers from index I to index j. Right? So initially it's 0, when j is I add ai, and so on. And I keep going forward. Now, this very simple improvement actually reduces our runtime by quite a lot. Now you can see that I have 2 nested for loops, so this is an algorithm with a runtime of n squared. Right? So our first improvement got us to O n squared. And hopefully if I don't have bugs anymore, which is embarrassing that I had a bug in such a simple problem anyway, we should be able to run this for much bigger instances. Okay, so let's actually start with an input of 10,000. And let's do this. And as you see, the previous one took a long time on 10,000. This one is almost instant. So n squared is really better than n cubed. But now let's say I do 10 to the power of 5. And I run it again. This is going to take some while. Yeah, my laptop is old. On a lot of modern laptops, it will probably do it faster. Yeah, okay, 10 seconds. And if I do 10 to the power of 6, that's hopeless. Now, can we do better? Well, some of you already know a linear time algorithm, but I'm going to take it to a divide and conquer algorithm now. So here's the idea. Let's say that I have my array, and let's just visualize it like this. So this is my entire array. Okay. And I want to somehow find a particular segment in this array that gives me the biggest possible sum. So I want to have a segment that is like, let's say, somewhere in the middle. I don't know where it is. That gives me the biggest possible sum. Now I can do a casework on this segment. I can say this segment is either entirely within the first half of the array, or entirely within the second half of the array, or it has part of it in the first half and part of it in the second half. So this is what I'm going to do. I take my array, I cut it down in the middle, and then I basically do a casework. So let's call this part the left side, this part the right side. My first case is that my answer, which is something that I have not found yet, it's just a segment that has the highest total sum. I'm going to say my first case is that the answer is in the left. Okay? Answer is entirely in left. Or the second case I can have is that my answer is entirely in the right-hand side. Or maybe the answer intersects both. Okay. Now, if it's entirely in the left-hand side, I can just recursively call my algorithm on the left side. Right? I have a smaller array. I can just implement my algorithm as a recursive function that calls itself on the left side. And then it's the same if it's on the right side. I can just call myself recursively. So if I want to write a pseudocode, this would be my pseudocode. So I have my MCS, I have an array A. Let's say I have a start index and an end index. So I have start index and an end index. And this is what I'm going to do. I'm going to say first, let my answer just be the answer on A if I go halfway. So I go from start to start plus end over 2. Okay. And then I say, let's call the same thing on the other half of the array. So this is basically the left half. I can also call it on the right half. So I say my answer becomes the maximum of whatever my answer was right now. And the answer on the same array, but now the right half. So from index start plus end over 2 plus 1 to index end. Okay? So this already covers the first two cases, but now I have to somehow figure out what is the best segment that intersects both halves. So what is the best segment that has some elements in the left half and some elements in the right half? But why is this easier? This is easier because I'm looking at segments and I know that I have an element from the left and an element from the right. So it means that whatever elements I have from the left are going to start from the middle going left until some point. And whatever elements I have in the right are going to start at the middle and just go right until some point. Right? So I can just try that. And by the way, the sum that I have on the left side is completely independent of the sum that I have on the right side. So I just start from this midpoint here. Actually, I have 2 pointers. I start from here, and I keep going left and keeping track of the maximum sum that I have seen until this point. And then I do the same thing. Start here, keep going right, and keep track of the maximum sum that you have seen until this point. And then just add them together. Okay? So if I want to write it here, it would be basically, let me give a name to this. I'm going to call this mid. I'm going to say sum left is 0 and sum right is 0. And then I ran out of page. I'm going to write it here, who cares? So I'm going to start at the midpoint and keep going left. So I'm going to say for every I, which is from the midpoint down to basically 1 or 0, based on whatever it is, or your starting point, just update the sum on the left-hand side. And also you need to remember what was the maximum amount that you saw, because this is the sum of the left-hand side from the middle until index I. But I want to remember what was the best I. Well, not the best I, but the value of the best I. So I do like a best left, which is 0, and a best right, which is also 0 initially. And then here I say best left becomes the maximum of whatever best left was, and sum left. And then do the same thing for right. I'm too lazy. Right? And then my answer would just be the maximum of whatever answer I had and best L plus best R. So if best L plus best R is bigger than the current answer that you have, make the answer best L plus best R. Okay. Let me code this fast. This would be not too hard. Actually, let me just copy this. Okay, I'm just going to say write the answer for the array A where the start index is 1 and the end index is n. and I'm going to have a function called MCS. It takes an array A, and it takes a start index and an end index. Okay, I'm going to say my middle is just start plus end divided by 2, and of course I have to be careful about the base cases. I have to say if my end is less than or equal to my start, I just return 0. Right? I forgot that in the pseudocode, but that's fine. I take my midpoint, and then I basically have to do this. I have to say my answer is going to be the maximum of the answer on the left-hand side and the answer on the right-hand side. So the answer on the left side is from start to the middle. The answer on the right side is from middle plus 1 to end. Right? And then I'm going to have these things. So sum on the left-hand side, sum on the right-hand side, best sum I found on the left, best sum I found on the right. And I'm just going to say for every I from mid to start, update the sum on the left-hand side, and best of left becomes maximum of best of left and sum of left. And then I have to do the same thing for the right-hand side. So from mid plus 1 to end, sum of the right-hand side increases by AI, and best of the right-hand side becomes max of best R. And finally, my answer becomes the maximum of whatever it was before, and best L plus best R, and I return it. Okay. What is my runtime now? So this is finally an interesting question. Let's first see if it's faster than the previous one. So I just run this, and so remember my previous case didn't work when I had 10 to the power of 6. So let me just create an input with 1, 2, 3, 4, 5, 6. Oh, actually, this is a bit weird. So let me make this whatever 10 to the power of 7, so that I do this. I create an input with 10 to the power of 7. 1, 2, 3, 4, 5, 6, 7. What's happening? It's taking time to even generate? What the hell? Okay, this is... Yeah. No, the code works. So this is just generating the input. This was the input generation thing that wasn't working. Yeah. Okay. Yeah, so let me give this to my MCS now, input.txt, and time it. Okay, nice. So this is now much faster than the previous one, but what is the actual runtime? And remember that I have the base cases here. Yes, someone said n log n, that's true. So I have to do base cases first. I'm just going to write it here, don't forget them. But let's just do another runtime analysis. So basically, let's say I use T of n to show my worst case runtime on an instance with n numbers. What am I doing? I'm taking my array and cutting it down to 2 arrays of the same size, n over 2, right? So T of n is 2 times T of n over 2 plus Well, what else am I doing? I'm starting at this midpoint, and I keep walking to the left and summing everything up, right? So how many steps am I taking? At most n over 2. I'm doing the same thing for the right side. I'm starting at the middle, taking steps to the right. And of course, I'm doing sums and maximums and all of those things, so I'm going to spend O(n) time. It's not exactly n, it's some constant times n. So my runtime is actually something like this. So T of n is 2T of n over 2 plus O(n). Now, if you want to be really pedantic about it, this should be like floor or ceiling of n over 2. I don't really care about that at this point. I will give you some YouTube videos to watch to know why you don't care about that. Okay. Now, I have this recurrence, and I want to solve this recurrence. I want to see what is the solution here. Now, those of you who have already seen merge sort know that this is the exact same recurrence that we had for merge sort, and the answer is n log n. But let's actually solve this. So let's look at our recurrence tree again, and by that I mean a tree that looks like this tree of the example for Fibonacci. Right? So here's what's going to happen. I'm going to start with an instance that has size n. I'm not going to draw the circles anymore. And I'm going to basically divide it into two instances, each of which has size n over 2. Right? And of course, additionally, I'm spending O(n) time here. So since this is O(n), what does it mean when a function is O(n)? It means that it's smaller than some constant times n. Right? So I can always say that there is a constant such that T of n is less than or equal to 2T of n over 2 plus that constant, let's call it C, times n. Right? That's how I'm getting rid of the O notation, because I don't want it to be there all the time. So I'm saying the extra time that you're spending going left and going right and doing all of these things, let's put a number to it. Let's say it's C times n at most. And I choose C large enough so that I'm sure I'm over approximating here. Okay, so I have an instance of size n, and I basically pay a cost of C times n to divide it to two instances of size n over 2. And then I do the same thing again. So here I pay a cost of C times n over 2, and here I'm also paying a cost of C times n over 2. And I'm doing that in order to break these into instances of size n over 4. Right? And then this continues. I break them down into instances of size n over 8 and so on, and I continue until my instances have size 1. And when they have size 1, I know my answer instantly. So this tree just continues. And basically, at every node of this tree, I know how much time cost I have. Basically, it's the size of the instance at that node times C. So I'm paying C times n units of time here to divide an instance of size n into two instances of size n over 2. And then for each of them, I'm paying C times n over 2 to divide them into instances of size n over 4. Then for each of those, I'm paying C times n over 4 to divide them into instances of size n over 8, and so on. Okay? So it's hard to fit everything here. I'm writing the costs in black, so I'm paying this much. Now, what is the height of this tree? How deep does this tree go? It's log n, because I'm starting with n, and my numbers are getting divided by 2 every time that I'm going down. So I can divide by 2 log n times. So this whole height of the tree, I'm actually going to just write O log n, because I don't care about, there's a plus 1, minus 1 somewhere, who cares? Right? So maybe it's log n plus 1. It's log n. Now, the next question is, how much time am I spending at every level of the tree? So you see, at this level, at the root level, I have only one problem. It's of size n, and I'm spending Cn time. Then at this next level, I have two problems of size n over 2, and I'm spending c times n over 2 on each of them. But that means that in total, I'm again spending c times n on this level. And this goes on. You can basically make an inductive argument that at every level, I'm spending c times n. So my total runtime is going to just be c times n times the number of levels, which is the height, and the height was log n. So my total runtime is going to be in O of n times log n. And again, I'm using O to suppress the constant factor c here. So you see, we went from an algorithm that had a cubic runtime to a better algorithm that had quadratic runtime, by just doing some things a little bit more cleverly, by just remembering not to recompute things that we already know. Then we had an even cleverer idea, and this idea of divide and conquer, this idea that I do casework, is it entirely in the first half, entirely in the second half, or straddles both halves? And that gave me an algorithm with a better runtime, with a runtime of n log n. Can we do better? Yes. So we can actually get rid of the log as well. And to do that, all you have to realize is this. Let's say I fix the endpoint of my solution. So this is our last algorithm here. Let's say this was my original array, and someone magically has told me that my j is here. Okay? Someone has told me that when I want to find the best possible answer, the endpoint is going to be here. Now, if that's the case, what is the best starting point that you can take? Yeah, so it's like I can look at basically all the prefixes, and I can look at the sums there. So let's say this is my array A. I create a new array B, where Bi is basically the sum of the first I elements in A. So it's sum of, let's say, k from 1 to I, ak. Okay? This is called the prefix sum. I'm just saying what is the sum of the first I elements in A. I call that Bi. Now, if I do this, the thing that I want to find here, this sum is basically the sum from I to j of the elements. But I can write this in terms of my array B, right? So this is just Bj minus Bi minus 1. Right? I'm just summing up all the numbers from the beginning to j, and then I'm removing the numbers that I didn't want from the beginning to I minus 1. So you see, as soon as I compute this array B, my problem becomes much simpler. My problem now is just find an I and j that maximizes Bj minus Bi minus 1. So now for any given j, I know exactly which value of I should use. I should use the value of I that gives me the smallest possible Bi minus 1. Right? Because I'm subtracting Bi minus 1. I want this Bi minus 1 that is being subtracted here to be as small as possible. So that's it. That's my algorithm. First compute the array B, and then just start from the beginning of the array B and go forward. Every time when you're at an index j, just remember what was the best or the smallest sum that you have seen before. And that's it. So let me do this. Let me copy MCS2 to MCS3. We have only 4 minutes. Now, I'm not going to do all of this. I'm just going to have another array B, which is going to be the sum of all the numbers in A, the prefix sum of the numbers in A. And actually, as I'm reading A, I can compute B. right? So every time when I read AI, I just say BI is AI plus AI minus 1. This was the very first idea that we had, that we don't recompute sums. Plus BI minus 1. So if BI minus 1 is already giving me the sum of all the numbers up until index I minus 1, I just add the number in index I, and that gives me the sum of numbers until index I. Now, great. So here's the thing. I want to see what is the smallest possible BI minus 1. Okay? So I'm going to have something called minimum B. And originally I put this as, if I get a negative 1, it will overwrite that. Because anyway, like B0 is 0, right? So I would just say that for every j from 1 to n, here's what I do. First, I say I want to update this minimum value of b that I have seen until this point. So if bj is less than min b becomes bj. Okay? And then, what is my answer? My answer was originally 0. The best possible answer that I can get, best possible answer ending at j, is what? It's bj minus min b. Right? So I'm just going to say, take that, bj minus min b. This is the best possible answer that ends at index j. But I want to see, is this really my best possible answer? Well, I'm going to take the maximum of this and whatever answer I had before. And I'm going to say my new answer is that. And finally, I'm going to write my answer. Okay. Now, this changes everything. Because now we have a linear time algorithm. We have an algorithm that is O(n). Look, I have a 4 from 1 to n, and I'm reading numbers in it and adding. So this part is definitely taking O(n) time, right? And here, again, I have another 4 from 1 to n, and I'm doing a constant amount of work in every iteration. In every iteration, I'm just doing some subtraction, maximum, comparison, so on, and like I'm doing at most 10 operations, let's say. So my total runtime, finally, is now just O(n). This is our best runtime. Is just O(n). And I cannot improve it any further. I cannot improve it any further because at the very least I have to read my input. And just reading my input. So this is, in that sense, an optimal algorithm. Okay, so that's it for today. I'll see you tomorrow.